All right, so we just discussed the fact that the nodes are spaced a half wavelength apart, and the antinodes are also spaced a half wavelength apart, and the antinodes, if this is 0, this is lambda over 4, lambda, this is half a lambda, 3/4 lambda, 1 lambda, so forth and so on. So there you go. Okay, now what we want to talk about, from the video, we saw that we only form standing waves at certain frequencies. So what we want to do now is we want to find these frequencies. Let's go to this again, or for the first time. So yeah, these strings, by the way, are somewhat elastic, so they stretch. Okay, so for this one, the length of the string is a half a wavelength. Here, the length of the string is 2 half wavelengths. Here, the length of the string is 3 half wavelengths, and so forth. So let's write that down. So we have the possible string lengths are lambda over 2, 2 lambda over 2, 3 lambda over 2, and so forth. So basically, all right, and we could write that, we can just say m lambda over 2, where now m is 1, 2, 3, and so forth and so on. So I always have to be, when you use m as an index, and there's nothing special about m, you can use any letter you want, but you got to be careful, you start it where you need it. So it's just a convenience. All right, so the length of the string is m lambda over 2. So there's different wavelengths, right? This is like lambda 1, lambda 2, lambda 3, lambda 4. So we want to somehow indicate that. So we'll put a little subscript m there. So let's solve for lambda m. So therefore, lambda m equals 2L over m. Okay, great. So all right, so lambda 1, 2L over 1, lambda 2, 2L over 2, and so forth. Now, this is wonderful, but who cares? We want to get frequencies. So remember, the most important equation with waves is, and I always call it F equals ma, is V equals F lambda. So let's use that. Solve for F. So F is V over lambda. Now, here's lambda. And we might as well put subscripts. What do you say? Because this is going to be like frequency 1, frequency 2, frequency 3. But we want 1 over lambda. So therefore, 1 over lambda m equals m over 2L. So let's use this and this. And what do we come up with? We come up with F sub m equals velocity. Let me write it differently. M times velocity over 2L. So there you go. So this allows us to figure out which frequencies to set our oscillator to obtain standing waves. So you see here, F1 is 1 times V over 2L. F2 is 2 times V over 2L. F3 is 3 times V over 2L. So that's a wonderful result. Now, we're doing this on a string. So instead of just putting V, let's put the velocity of a wave on a string. So we learned this a while ago. Right? That's the velocity of a wave on a string. Let's put that in there. So now we have Fm equals m times 1 over 2L square root T over mu. Ta-da! So there you go. And again, m equals 1, 2, 3, so forth and so on. If you listen carefully to that YouTube video, the narrator talked about a fundamental frequency. The fundamental frequency is F1. And you know, that's just 1 over 2L for a string Ts over mu. And then, so basically, this is F1, right? This is F1. So then we can just say that Fm is just m times F1. And that's what the narrator on that video pointed out. He said, you know, once you find the fundamental frequency, it's easy to find these because, let's say this is 10 for the 10 hertz. Well, this is going to be 20 hertz, 30 hertz, 40 hertz, and so forth and so on. So that's why whenever you're doing this kind of a demonstration with the standing waves, the first thing you want to find is the fundamental. Once you find the fundamental, then the other is a piece of cake. All right. So there it is. So now we know these are the frequencies, right? These are the frequencies where you obtain standing waves. So think about what we've done. We figured out the positions of the nodes. We figured out the positions of the antinodes. We figured out the frequencies to make standing waves. So we've solved the problem just using waves. Now, in the real world, here's a violin. Let's use what we've just learned. How does a violin produce different sounds? And of course, what's a sound is a frequency. So how does a violin produce different frequencies? Well, you know, here's the equation, right? That's the equation. So what do they do, you know? Well, let's see. There's an L here. Looks like the L's are pretty much the same. There's a T, a tension. And, you know, if you know something about violins, the tensions can't vary very much or you'd break the violin. So what do? Well, they have different mu's, right? Different mass densities. So it looks to me like this string is thicker than that string. And then also when the violinist is playing, you know, they're holding the string at various places. So where they put their hands, they're kind of like changing the effective length of the string. So that's how they do it. Something that's closer to home is a microwave. So a microwave oven sets up standing waves, wavelength 12.2 centimeters, a wavelength that is strongly absorbed by the water in food, and most foods have water in them, so this is a good thing to do. Because the wave has nodes spaced lambda over 2 or 6.1 centimeters apart, the food must be rotated while cooking. Otherwise, the portion that lies at a node where the wave amplitude is 0 will remain cold. So I remember when microwaves were first introduced, and the very first ones didn't have a turntable. So that means that if you didn't want to have hot spots and cold spots, you had to keep turning the microwave off and on and moving it. And then, you know, after the first year or so, somebody finally thought, hey, let's put a turntable in there. So there you go, standing waves in a microwave. Okay, so here's a question. This standing wave has a period of 8 milliseconds. Draw snapshot graphs of the string every 1 millisecond from 1 to 8. Okay, now let's not do any math. Let's just think about it. The period is 8 milliseconds. So this is what it looks like at 0. So therefore, what's going to look like at 8? Well, the same thing, right? It's going to look exactly the same. Okay, what's it going to look like a half a period later? Well, remember, this is what it looks like at 0 and 8. So what's going to look like a half? Well, it's going to be like that, right? Okay, let's just show you. Oops. Okay. So here we are at 0, and this is 1 period later, so it's the same. Okay, a half period is just going to be opposite, right? So it's going to be like that. This is 4 milliseconds. Okay, now, what's going to look like just a little bit after 4? Well, let's go over here. So this is 0. This is 1, right? So the amplitude is getting smaller. Okay, this is 4. So this is 3. So what's going to be between this and this? Well, obviously like that, right? Let's do that again. Let's go over here. So here, what's it going to look like a millisecond after? Like this. Here, what's going to look like a millisecond before? Like that. So what's going to be halfway between this and this? Just straight. So anyway, there you go. All right. So kind of picture that in your head, to see how these, and again, it's supposed to look like this, right? All right, so anyway, think about that. Make sure it makes some sense to you. All right, now we're going to we're going to shift gears. Now what we're going to do is okay, so that was transverse waves, right? Transverse waves on a string. But remember, there's another kind of wave, which is called a longitudinal wave. And where are they found? Sound waves, sound waves in air. So now we're going to talk about standing sound waves in an air column. And again, these are longitudinal waves. And this is just to remind you what a longitudinal wave is, right? You have a string and you kind of push it or pull it, right? That's a longitudinal wave. Now, once again, you better pay attention because you're going to be doing this on your exams, in your labs, in your homework, and I'm not going to give you the equations. You have to be able to figure it out. And you're going to see it's easy to figure out. It's not so bad. All right, so this is no sound wave. This is just normal air, atmospheric pressure, so we're assuming that these are air molecules, So there's, like I said, there's nothing disturbing them, there's uniform pressure, so they're just spaced evenly, Nothing's really going on, not very exciting. All right, the next thing, though, all right, so that's just kind of like to give us a reference point. Okay, now what we want to talk about is called a closed column of air. And again, it's just to help us figure it out. So we want a closed column of air. So just what it says, right? This is a column of air with closed ends, right? So the air is stuck. Okay, it can't get out, can't get in. All right? And the length of this thing is L. All right? Now, look. This is, it's closed here. So the air can't get out, right? So this air, it can't oscillate because it can't get out. Same thing here. I mean, the air can't move past this end cap, and so the air can't move right here. So if the air can't move here, and it can't move there, or it can't oscillate, if you want me to say that, what is this, a node or an antinode? Well, it's a node, right? A node is no oscillation. Okay, now we've got to add an adjective. You'll see why in a minute. So we're talking about displacement, right? Displacement. So these are really displacement nodes. Displacement nodes. Okay, now what we want to do is we want to introduce a sound wave, a longitudinal sound wave. Let's just say at time equals 0. Now this is how you draw it. Now you've got to be careful. This is not a transverse wave, right? With a transverse wave, you draw what you see. But this is not. This is a longitudinal wave, so you've got to kind of be careful. So what does this mean? So this is x. This is the length of the air column or whatever, length L. But this is the delta x. So here's your sound wave. But what does it mean? It means that this part of the air has a positive displacement. So it's being pushed to the right, right? Positive delta x. It means that the air is pushed to the right. Now here, it's pushed negative, which we're saying is to the left. So this air to this half of the air column is pushed to the left. All right, now think about it. I mean, you have this air column, You have an air column. And this air is being pushed to the right. This air is being pushed to the left. So think about pressure now, okay? Think about pressure. Where are you going to have the maximum amount of air pressure? In the middle. Agree? The middle. Okay, so here you go. All right, so again, this is being pushed to the right. This is being pushed to the left. So you're going to have a lot of pressure here. Not so much pressure here. Not so much pressure here. Okay, so what am I talking about? I mean, when you talk about pressure, you've got to relate it to something. So what we're saying is we're relating it to atmospheric pressure. So we're saying here the pressure is greater than atmospheric. Here and here it's less than atmospheric. All right, so that's all right. Okay. So what we say then. Okay, good enough. That's good enough. All right. Now what we want to talk about, since that's a t equals 0, right? Now let's do it at a half a period, okay? A half a period. So just what we saw earlier, right? You know, initially it was like this, then a half a period later it flips, so it's like that. So what does this mean? It means that this air in the here is being pushed to the left, and here the air in this half is being pushed to the right. Okay, well, if that's the case, you can have high pressure here, low pressure here, right? Okay, so like I said, high pressure here, low pressure here. All right, now, okay, so we did time equals 0, then we did time half a period. Now let's do time a fourth of a period. Now just think about it. So here was this was time equals 0. This, hold on a second. This was time equals half a period. So what do you think it's going to look like at a fourth of a period? Well, we did that example, right? So time equals a fourth of a period, just going to be straight, right? Just going to be straight. So that's, okay, so like I said, that's time equals 0, time equals half a period, so time equals a fourth of a period. Like I just indicated, it's going to be straight, right? So there's no displacement, everything just looks, you know, like it did when we just had regular normal air. Okay, so let's kind of put this together. At time equals 0, you know, we had, at time equals 0, we had, okay, displacement, node, node, node. But look at the pressure, though. We had max here, we had min here, we had min here, right? So like this is like a pressure antinode, pressure antinode, pressure antinode. So it seems that the displacement nodes occur at where the pressure antinodes occur. How about t equals a half a period? Okay, here again, node, okay, displacement, right? Displacement node, node, node. But look, here's max pressure. That's pressure antinode. Here we had min pressure, pressure antinode. Max pressure, just pressure antinode. So it just seems you have to admit that the pressure nodes, or let's do it the other way. The displacement nodes occur where the pressure antinodes occur. So they're interchanged. Okay? All right. So here, this is now we're putting everything together, right? So here's the displacement node, pressure antinode. Displacement antinode, pressure node. Displacement node, displacement antinode, and so forth. So here's the important thing. The displacement and pressure nodes and antinodes are interchanged. That's the important thing. They're interchanged. All right. And again, this is for closed, because we couldn't have, the air can't oscillate. Now, where have you seen that before? Where have you seen that before? Well, looks to me like a m equals 2 for a string, right? A m equals 2 standing wave on a string. All right. So guess what? All right, there it is, yeah? Okay, so here it is, okay? So for m equals 1, okay, so this is the m equals 2 we just talked about, right? So for m equals 2, here's the displacement graph in the blue. Well, what's it going to be for m equals 1? Right? Node, node. What's going to be for m equals 3? Node and node. Now, you don't have to memorize this. It's simple to think about. Okay, so here's your air column. Let's make 3 of them. Okay, now remember, these places have to be displacement nodes because the air can't move here because there's an end cap. All right? So you just have to draw it properly. So if that's a node and that's a node, what's the smallest wavelength, I guess the biggest wavelength you can fit in there? Well, it's going to be like this, right? I mean, right? Now, what's the next one? I mean, what's the next one? Again, this has to be a node. This has to be a node. So the only way you can do it is like this. Pretty pathetic drawing, I guess. Right? So this is m equals 1 hump, or whatever. This is m equals 2. Okay, again, has to be a node. Well, what's the next one going to be? It's going to be 3. So 1, 2, 3, 1, 2, 3. I mean, right? It's supposed to be like this, right? But I think it's just easier drawn the other way. So that's m equals 3. So, you don't have to do a lot of thinking. You just make these nodes and just figure out how many, just stick out how many humps you can get in there. That's all. Honest, that's all there is to it. And then if they ask you to draw the pressure, it's just opposite. So here's a displacement node, you put a pressure antinode. Here's a displacement antinode, you put a pressure node. Bingo. So in my opinion, I would always draw the displacement curves first. And then once you have those, then draw the pressure graphs. So there it is, that's all. All right. Okay, now, there you go. Closed, closed. Now, I'm not a musician, but I don't know any musical instruments that are closed, closed. So what we want to talk about now are some real musical instruments. So let's talk about organ pipes. All right, organ pipes are open, closed. So here it's open. So that means the air can go like this, right? And it's closed, so the air can't oscillate. So you don't have to do anything fancy. You don't have to do anything fancy at all. Let's just think about the displacement. Here, this has to be a displacement antinode. Here's a displacement node. Draw the largest wavelength you can think of. Well, antinode, node. Okay, that's m equals 1. Now, for the next one, do it again. See what you can fit in here. Well, I mean, you can't get m equals 3. You can't get m equals 2, right? If this is going to be an antinode and this is a node, I mean, this is it, right? I mean, what else can you fit in there? So this is what I'm talking about. So open, closed. So for this one, this is an antinode. This is a node. So right, that's all you can say. For this one, again, this is an antinode. This is a node. So how many half wavelengths can you stick in there, or quarter wavelengths or whatever? I mean, this is all you can really do, right? Try to get something smaller than that. You can't. So for this one, here's this guy, and then that one, and then that one. I'm not drawing these to scale, but I hope you understand. So here, this is 1. And by the way, how much of a wavelength is that? It's a fourth. Agree? This is a fourth of a wavelength. Okay, here's a fourth. This is a half, so that's 3/4. Okay, let's do that. So we have a fourth of a wavelength. Here we have 3/4 of a wavelength. Here, this is 4/4 plus a 1 is 5/4. All right, so this is lambda over 4. This is 3 lambda over 4. This is 5 lambda over 4. So this is m equals 3, m equals 5. Okay, I mean, that's it. So this is the length. This is the length of the column, right? All right, so let's work it out. So we have, so lambda m appears to be 4L, right? 4L divided by M, where M, 1, 3, 5, so forth and so on. All right? So now, V equals F lambda. Okay, so 1 over lambda is M over 4L. So this is going to, so we want frequency. So frequency is V over lambda. So it's V, so sorry, MV over 4L. Ta-da. So these are the frequencies you can get with an open close. Now notice, here's the important thing. You only get odd harmonics, right? It's not where there's, it's not like M equals 1, 2, 3, 4, 5 like the other one. It's only odd harmonics. That's all you can get. All right, now let's do wind. Okay, wind instruments are open, open. Now again, you don't get all, you just draw the picture. You can draw the pictures. You can draw the picture. You can get all these, do all this derivations, which you'll have to do in a lab, and maybe tests or homework. All right, so just convince yourself it's easy. Okay, open, 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 open. All right, if it's open, air can oscillate. So if air can oscillate, it has to be the displacement antinode. Now remember, we're trying to draw wavelengths, right? So what's the largest wavelength you can get in here? Well, this is a displacement antinode. This is a displacement antinode. So what do you got to draw? I mean, the only way you can do it, so this is how I do it. I just go like this, right? I mean, pretty awful. That's supposed to be this. Okay? What else can you do? All right, for the next one, again, you want to try to fit as many, the smallest number of wavelengths as you can. So here, you're going to kind of go like this, and then like that. Because what else can you do? I mean, you can't get any, you can't get any smaller. And then the next one's just a total disaster, right? So you have 1, 2. All right, and you can just keep going. So all I'm saying is, you don't have to do a whole lot of thinking. All you have to do is make sure that if it's open, there's a displacement antinode. And then just keep adding and adding and adding and adding. That's all you have to do. And if you want to draw the pressure, just remember the pressure is interchanged with the displacement. All right, that's it. It's not so bad. Just drawing silly pictures. All right, let's do it. So what's the length? Okay, how much of a wavelength is this? Remember now, here's a wavelength, right? So what's just this part? Not just this, right? That's just lambda over 4. So this is lambda over 4. This is lambda over 4. So we just have 2 lambda over 4. So lambda over 2. Okay, let's do this one. All right, this is lambda over 4. This is lambda over 4. This is half a lambda. So we just have lambda, right? So we have 2 lambda over 2. Okay, this one. So this whole thing is a wavelength. This is one wavelength. This is a fourth of a wavelength. That's a fourth. So 1 plus a fourth is 1.5. So we have 3 lambda over 2. See how easy it is? You're just drawing pictures, All right. So then we have the length is m lambda over 2, right? That's all. So therefore, let me write that up here. So the length is m lambda over 2. So therefore, solve for lambda. So lambda equals 2L over m. And what's m, by the way? 1, 2, 3, and so forth and so on, right? Okay, V equals F lambda. So F is V over lambda. Okay, 1 over lambda is m over 2L. Therefore, F equals V times that. So mV over 2L. Ta-da! And again, m is 1, 2, 3, so I have even and odd harmonics. All right, now look, you have to make sure that you can draw the pictures for the closed, closed, the open, closed, and the open, open. You have to be able to draw, and just concentrate on the displacement graphs. You have to be able to draw those. And that's not enough, though. Once you've drawn them, you have to be able to go through this analysis, right? Like L is a half a wavelength or whatever, you know. You have to be able to go through this analysis to figure out how the length of the air column with respect to the wavelengths. Then you have to write something like this. Use F equals ma, solve for frequency. So you should be able to figure out, without looking at a book, the frequencies for closed, closed, open, closed, and open, open. You have to be able to do that. So take the time to convince yourself you can do that. Okay, let's quit.